And we work with a lot of data, primarily in the financial services industry, and we work with a lot of algorithms and try to understand the nature of the data and help mostly quants figure out what they should be doing with their data sets. And I also have a teaching position at Babson College, and I also teach a data science course at Northeastern University. And primarily, the goal of this presentation is to give you an orientation on various data reduction techniques which are out there. This one's not going to be very mathematical, so if there are PhD scientists out in here who wants to kind of look at the algorithms and kind of comment on the algorithms, you'll be disappointed because there are no equations in this presentation. It's going to be more of an orientation on what all you could do with the various data reduction techniques which are out there. How many of you are data scientists, practicing data scientists? And how many of you are aspiring data scientists? How many of you deal with large amounts of data? How many of you deal with a large amount of dimensions in your data sets? And it looks like I'm getting an even answer. It's like 50-50, 50-50 kind of thing. So it's good. It's a good representation. And if there are things which are in this presentation you would like to talk to me more about in detail, I'll be available after the presentation, and I can give you more information and pointers. So everyone knows about large data sets, big data, data science, and you've been listening to various presentations throughout the day. My goal is to kind of give you like a roadmap on what are all the methods which are out there which you could use and explore to see how you can reduce the data. Okay? Now, I don't want to get into the infrastructure part on how do you actually take large data sets and slice it and dice it and put Hadoop and various components out there. I want to take another approach. I want to tell you what are the various mechanisms out there which has been formalized and scientifically developed over the years, which you could use in conjunction with various technologies which are out there so that you can take these data sets, reduce them, and bring it into a shape which you can actually use it in your analysis. So I'm not going to differentiate between big data and small data, but primarily this is going to be about high dimensional and large data sets, which you would be interested in kind of summarizing so that you can start processing these data sets. Now, how many of you read this article in the New York Times? It's one of the popular articles which has been doing its rounds. So the summary is that all aspiring data scientists and practicing data scientists would watch that you would want to do the fun part. The fun part, which is kind of using the algorithms, get to the analysis, get to the insights, make those insightful decisions, and say, okay, this is how we got in value. But the reality is, 70% of the time you're dealing with bad data, you're dealing with missing data, you're dealing with large amounts of dimensions, and you're spending most of your time trying to figure out how do you take all these data sets and then bring it into a shape where you can actually get to use your algorithms and make specific decisions, right? How many of you like the proverbial janitorial work which is mentioned in this article? You like it? Well, I need to talk to you because we have a lot of those kinds of things. I used to work at Indica before, and we used to build these data pipelines and just processing all these data sets and trying to get to a shape where we could actually get our clients to see what the end results would look like was such a big task. And my goal is to see, well, how do we make those 60 to 70% of the job easier? How do we try and use some of the mechanisms and make sure that we can get to the fun part as soon as possible? I wrote an article a couple of months ago called Gaining the Technology Edge. So here, what I want to emphasize is there are two ways in which you can approach high-dimensional data problems. One is to say, let's leverage technology. Let's leverage infrastructure. Let's leverage multi-core processors. Let's leverage large amounts of RAM. Let's just throw in resources at the problem, and then try and see if we can leverage all the insights we're going to get after using all the technology. Because the argument is, well, hardware is cheap. Why not just leverage the hardware and use the hardware, right? But the alternate argument is, well, there are also mechanisms you could use. And if you intelligently start looking at data even before you can get to the processing part, you can get a lot more value from your data analysis task by just making sure that you have those insights even before you can start using those predictive analytics algorithms. So I want to give you a 3-step roadmap, and I'll give you references. Most of the stuff I'm going to be talking today are published in textbooks, so I'll give you references so that you can read about each one of these materials. So I want to kind of differentiate 3 things. One is in data reduction. Let's talk about dimensionality in data. Let's talk about numerosity reduction, and let's talk about compression. And I'll talk about each one of these 3 aspects and talk about various techniques on how to go about it. So first of all, let's talk about what is dimensionality, right? How many of you know about the curse of dimensionality? I know most of you know, at least some of you have heard about it. So the notion is, when you have multiple dimensions in data, you have to factor in that. So let's take the first picture in here on the left. So there are 9 data points in here. And if you put those 9 data points, or rather, if you put them on a 3x3 grid, this is what you see. But if you start going from a 2-dimensional space to a 3-dimensional space, you can see that the data starts becoming more and more sparser. So if you want to build models which can factor in, or we can make sure that you can factor in all the dimensions in your data, you need to have a lot more data. So that's kind of the challenge you're dealing with. When you are dealing with really large dimensional data, if you start, this is up to 3 dimensions, but if you think about an n-dimensional grid, you will see that the data is going to be very, very sparse in this n-dimensional grid. What that means is you have to think about ways in which you can kind of summarize the data or reduce the data so that you can start getting insights out of it. So what is the best way to go about addressing this problem? Well, there are multiple dimension reduction techniques you can use even before you can start applying your predictive analytics algorithms. And I typically bucket them into 2 segments. One's what's called as a variable selection methodology, and another one is what's called as a variable reduction methodology. How many of you have heard these terms before? Some of you have heard. OK, let's talk about how do we go about addressing dimension reduction. So when I talk about dimension reduction, think about a matrix, right? Your x-axis is all the dimensions you have, and your y-axis is all the data you have, right? So you have multiple data points. Let's assume that the data sets are cross-sectional in nature, so which means that there's no temporal nature in the data. There's no time series data. You can mix and match the rows. So you have a lot of rows and a lot of columns, OK? So the columns, if you have a lot of columns, it means that you have a lot of dimensions in your data. And the goal in dimension reduction is to see how can you reduce the number of columns so that you can have fewer number of columns and get most of the information in the large number of columns in a fewer number of columns. OK? So in variable selection, the goal is to see, well, do we, first of all, need all these dimensions? Do we need all these columns? How about we select fewer number of columns and see if we can get all the insights we need from these fewer number of columns? Okay? So that's what the goal of variable selection is. And is there a possibility that we can remove some of the columns which are not relevant and unnecessary in these data sets? And I'll talk about 2 methodologies you could use in order to do that. One is planar regression. How many of you know regression? Now, most of you know regression. And we'll also talk about decision trees, which could be used for variable selection. OK. In regression, what you do is you basically say, OK, I have all these columns I could use as predictors. And I want to get my prediction as a function of all these predictors, right? In variable selection, what you try to do is say, how about we use algorithmic techniques to figure out what are the minimum required number of variables which would be needed to actually build a regression model, which will kind of have a similar representation as though you had all these columns. Okay? And there are a couple of methodologies you could use in here. One's what's called as an exhaustive search. Now, I'm not going to be talking about computational complexity in here. I'm going to be only talking about dimension reductions, and we'll touch upon some computational issues. But exhaustive search is basically saying, what in case I can have a mechanism of choosing all potential possibilities of my variables and building regression models and select the one which gives me the best possible model with a parsimonious model with the fewest number of variables. Okay? So if I have the computational power to basically say, let's go through all possible combinations of columns and come up with all potential regression equations, and then choose the one which gives me the best possible error metric or whatever I'm using to choose my regression equation. So that's exhaustive search. Obviously, that's very expensive, because if you have to go through all these combinations, you have to spend a lot of computational power. So there are some suboptimal solutions. One's what's called as forward selection method, when you start with one variable, and then you say, OK, how about I add the next variable, and you start adding more variables to your equation, and stop at a point where adding a next variable doesn't give you much value for your regression equation. So the problem here is, because you're not covering the entire space of possibilities, you may not get the optimal regression equation. Okay? You may get a good solution, but you may not get the optimal solution. What you can do otherwise is go for a backward selection mode, wherein you first of all say, let me include everything into my regression equation, and then I stop dropping one at a time, and see if I can get to a point wherein I can drop enough number of variables, and I can still maintain a regression equation which gives me potential predictive power. And then there's stepwise regression, wherein you keep on adding and dropping the one which is not very good, and then kind of come up to the best possible solution. Obviously, the exhaustive search will be the best one, but it's going to be the most computational one. But you can use a technique like this rather than just fitting a regression equation. Many software packages have mechanisms which are inbuilt into it. So if you have the computational power, you can go about using some of these techniques by doing what's called as variable selection, which is only focusing on the variables of interest and excluding the ones which you are not going to be using for your predictive power. Okay? Another method of going about doing a similar thing is using decision trees. There are multiple methodologies by which you can build decision trees. And the goal is, how about we build a decision tree with the fewest number of variables, which will give me the results I'm going to be looking for. So here, if I have, like, let's say, 1,000 variables, but there are only 10 or 15 variables I can logically use to make my decisions, how about I build a decision tree to get to those variables is the problem statement we're having. So here, there are multiple methodologies you could use. One is what's called as a CART, which is a classification and regression tree algorithm. There's another one called C45. There's random forest, which is pretty popular. So you can use mechanisms like these, and you can reduce the variable space and only focus on the variables which would be of interest. Okay? Now, if you want to also look at other ways of reducing your variable space. Now, the variable selection basically means that you can see all your variables even in your final solution, right? And you will be choosing a subset of all potential variables to build your regression or your decision trees for your solutions. But there are other methodologies which you could use to actually reduce the variable space at the cost of not having the transparency and not having the visibility of what the variables are going to be in your final solution. So some of these methodologies are wavelet transforms, PCA, or principal component analysis, and factor analysis. So let's talk a little bit about that. So in wavelet transforms, what you do is, if you have a vector of potential variables, you come up with another vector which represents the wavelet transforms for the original vector set. And then what you do is you eliminate a portion of these variables and only retain a set of these variables, which will be representative of your lower dimensional variable set. Okay? So just to give you an example, so this is like a 2D wavelet transform for a JPEG 2000 algorithm. So this is like the original image, and here you can see how you can reduce that into a fewer number of dimensions using wavelet transforms. There are multiple, this is a signal processing techniques. If there are electrical engineers in the room, you'll probably appreciate this. So it's basically a signal processing technique to reduce the number of dimensions in the space. The other methodology, which is pretty popular, is what's called as principal component analysis. So here, what you do is, if there are multiple variables which are highly correlated, so what you do is you take all these large set of variables and you reduce it into a smaller set of variables. And the goal is you want to maintain the variability of the larger variable set into a smaller set of variables. Okay? What happens when you do your principal component analysis is you are basically going to get a set of weights which you're going to be using to build your final equations. But the problem is, when you see your principal component weights, you are not going to be seeing the actual representation of the variables. Okay? So the intuition is gone, but you can still maintain the variability in a fewer set of components. But it works surprisingly well for sparse data sets. So if you have a lot of sparse data, you can use principal component analysis and get a fewer number of components to actually see if you can use that for your problem sets. Now, another methodology which is used, and primarily in finance, is what's called as factor analysis. So here what you do is, if you observe that in your data sets, there are multiple variables which are kind of similar in nature, but you could use some kind of a linear combination of a bunch of variables and have another variable represent these variables. You're basically chunking some of these variables which look similar or which behave similarly and replace that with what's called as a hidden or a latent factor. Okay? So you basically take your entire variable space and look for those variables which are kind of similar and then kind of reduce them and build these hidden factors and then use these hidden factors instead of the original variables. Okay? So this is another way of reducing your dimension space, and you'll be left with these hidden factors which are not probably very intuitive, but you would have reduced your variable space. Okay? Now, the other technique which, so we talked about variable reduction and variable selection. So if your goal is to say, okay, how about we reduce the number of columns? One thing you could do is say, well, at the cost of losing the intuition, can I try any of these methodologies like PCA or even SVD or factor analysis and come up with methodologies by which you can reduce the number of dimensions and work with that? If you are not ready to lose the intuition, if you would like to retain the original variables, many times in business decisions, when you build a model, you would like to see those variables in your final model. That way you can have a gut feel whether these variables actually make sense. Then you would want to go for variable selection, wherein you select those variables into your final equation. Okay? So that's basically a summary of some of the dimension reduction techniques you could use. The second methodology you could use for data reduction is what's called as a numerosity reduction. So here, there are a couple of methods you could use. So the first method is what's called as a parametric method. So here we'll go back as an example to the regression equation, wherein your goal is to say, well, in certain cases, I don't really need to work with the data. I can work with the representation of the data. Basically, I can work with a model which has been tuned to represent the original data set. So at that point, what you could do is you could just build a regression equation and use this regression equation to actually model the data. Okay? So here you're using a parametric methodology, which means that you are seeing the original parameter, the predictor variables, and you're creating a response variable, and you're using this methodology to actually reduce the number of variables and come up with this way of reducing the number of variables. Another way, so as you know, this is basically extendable to multilinear regression. So if you have multiple variables, you can definitely extend it to multilinear regression. Now, another way is to see if you can use non-parametric methods. And this is where some of the art comes in. Okay? Because here you can't just use automated and computational methodologies. Here's where you can do interesting things, like playing with the data. So this is a methodology you could just use binning. So for example, here you have, on your x-axis you have price, and on your y-axis you have counts. So you basically generate a histogram of your data, and then say, you know what, I don't need the granularity at this particular level. So how about I do binning so that I get fewer buckets and use these fewer buckets for my analysis? Okay? So that's a very easy way of, once you plot out your data, you say, you know what, I can live with just 3 buckets instead of having 10 different representations on 10 different buckets. So if you have prices or if you have ratings and things like that, you can start doing interesting things like this by using binning to reduce the amount of data you have. Another methodology you could use is basically clustering. So you could build clusters of your data even before you could do any analysis and use these cluster representations as variables in your data. Okay? So this would require maybe some graphical techniques wherein you plot out the data and see if you can find out where these buckets are. Or you could use some of the automated methods, k-means or hierarchical clustering or whatever it is, to use distance measures to cluster these data sets and then say, OK, how about I bucket them even before I can start using for other data analysis. And another way is sampling. Sampling sometimes doesn't get the recognition it deserves, but you could do very interesting things with sampling. This is a well-known statistical technique. So on the top you have sampling with replacement and sampling without replacement. So if you are just looking for sample data, and you can just get a random number generator and get some sample data sets and see and explore what the data is, and then see if you can make some assumptions on the data and then start using other data techniques with the larger data sets you have. Sometimes a sample may be sufficient. You may not need to have the entire data set to do your analysis. The second way is to do what's called as a cluster sample, wherein if you have slices of data, you may not need the entire slice. You may just need, rather you may not need the entire set of slices. You may need a couple of slices, and then choose a couple of slices to do your analysis, and then figure out if that's going to be sufficient or you would need the entire data sets. And lastly, you could use stratified sampling. Stratified sampling is a way by which you could say, you know what, I see different data points for different classes. So how about I choose some data points from each one of these classes, so have sample representations from these data sets, and use a smaller sample to first build intuition, and then go back and build my final model. Remember, many of the things I'm talking about here are not straightforward. It requires a lot of experimentation. But I'm talking about exploratory data analysis in here, wherein you're taking a large amount of data, trying to figure out how you can reduce it and get some intuition, and then start using this to start building better models. The last one is aggregation. So here, you may not require the temporal nature of data. So you may need to aggregate it at smaller, into smaller aggregates, and then you could use the data at a higher level of aggregation rather than at a granular level. Okay? The last thing I want to talk about is compression. Compression also could be an interesting way of using even before you start doing your analysis. So if you start working on the cloud, one of the challenges you'll deal with is transporting the data. You may have the computational power, but when you're transporting the data, that may take quite a bit of time, and you may not need to transport the entire data set sometimes. So sometimes you could use, there are two methodologies here. One is what's called as a lossless compression. So an example would be a zip file. So here you're packaging the whole thing and then sending on to another place where computation is done. There you unzip it, and then you do your computations, wherein you are getting back the entire data set there. But here you're saving on number of bits you're actually sending through the wire. And then there is lossy compression, wherein you may have to do some processing beforehand. You may not need the entire granularity of the data sets. If you're capturing using some sensors, or if you're capturing images, you may not need the entire granularity. You may need to do some kind of pre-processing, and you would do the compression, and then save only the compressed data, and then use it for your final analysis. Okay? So basically, this is kind of the roadmap we walked through. Okay? So there are three methodologies. One is dimensionality, numerosity reduction, and compression. And in dimensionality, you can use variable selection and variable reduction. And then in variable selection, you could use either decision trees or regression methodologies. And in variable reduction, you could use PCA, factor analysis, or wavelet transforms. And for numerosity reduction, there are parametric and non-parametric methods you could use. And for compression, you could use lossy or lossless compression. Okay? So the summary is, you can still maintain the integrity of the data even by reducing the data sets. So data reduction sometimes does not get the recognition it deserves when you do data analysis. People want to jump into algorithms and try out various algorithms even before they look at what kind of data sets they have. So I'd highly recommend incorporating data reduction as a part of your data lifecycle and data workflow to make sure that you understand the nature of the data before you can start processing those data sets. And it's not easy to just choose a methodology and say, this is the methodology I'm going to be using. You have to get familiarity with all these techniques and understand which ones are good from a computational perspective, which ones are good for sparse data sets, which ones are good for high-dimensional data sets, and choose the appropriate methodology. And it also depends on the use cases. If you would like to have the transparency and the visibility of the actual variables, or can you let go of those visibility of the data? And then you can, you will also need to factor in the computational complexity, whether you would have the processing power to do this pre-processing, or would you as well just use all the data and then do the processing directly rather than doing the pre-processing before you can go ahead and do the final data analysis. So that's kind of the presentation I had. And I'll open it up for questions. And by the way, many of the things I showed you, they are very well documented in these books. So if you're interested, and when I share the slides, you can just take a look at these books and get some more information on these topics. And I also have an article in the Wilmot magazine, and I'll share the link. So this article goes in much more detail about many of the techniques we discussed early in the presentation. Okay? Thank you very much, and I'll open it up for questions. Yes, please. Well, so you will have to use the technology which is appropriate for the kinds of data sets you have. So if there are techniques which are not applicable for the data sets you have, you are unfortunately not eligible to use it. Sometimes if you have categorical data, you may be able to convert it into numerical data. And if you are able to do it beforehand, that's a good way of transforming the data even before you can use a technique. But if you have to maintain the granularity of the data in the classes you would need to have, then unfortunately you may not be able to use some of the techniques in there. Well, so the thing is, dummy variable is one way of using zeros and ones. If you're talking about regression, you can definitely transform a categorical variable into a numerical variable, right? You can just use a dummy variable. If you have multiple classes, then you're, I think there's the method called all or none, so you kind of use multiple methodologies if you want to do classification with multiple classes. But some of the techniques, you may be stuck with continuous data. But some methods work well with continuous data, and some of them may not be appropriate for categorical data at all. Yeah. Yes, please. Right. Sure. Yeah. So the thing is, it depends on. So after you do your PCA, you have to definitely do your analysis. So figuring out how many components do I need, and what amount of variability are you going to be capturing, right? So sometimes when you do your PCA, if the data is such that you may have to retain most of the components, then obviously PCA may not be a valid process at that time. You may as well just retain the original data. But at times, you may have that it's all in the data, right? So you may have data sets wherein you may get most of the variability captured in the first two columns itself. At that point, it may be a very good technique to have. Mm-hmm. You could get, you'll have to do a little more, I guess, let me put it this way. As a statistician, you can go in and understand the nature of these loadings and figure out, what may be happening in there. But I guess the concept I'm bringing in here is if your goal is just dimension reduction and not really understanding the nature of these factors, then, if you're understanding it from a data representation perspective, that's probably a good way to do it. But if you're trying to just reduce these dimensions, then you may not have the bandwidth to kind of go in and do that analysis. You may as well just process the data. Yeah. Yes, please. That's an excellent question. So the question was, if there are 10,000 values as categories, what's a good way of looking at it? So one thought could be using some sampling techniques, right? So if you're looking at zip codes, can you have sample zip codes which represent various regimes, right? So if you can use things like stratified sampling, wherein you are maybe choosing a zip code from a particular area to represent maybe a disease or some kind of a thing from that particular population. So therein, sampling could be one technique you could use. The other technique you could use is aggregation. So if you could maybe bucket some of these zip codes into maybe a representation of Massachusetts or a representation of the Middlesex County or whatever it is, that way you're doing higher level of aggregation. That way you are reducing the number of data points you have. So that's another way you could try and do things. So those are some of the things which come off the top of my head, but I can give it a little more thought and maybe talk to you later. Any other questions? Thank you very much.